So, what we're looking at is chapter 12, which is now our electrophilic or electrophile edition, I should say. Our electrophile editions are really, I would argue, split into kind of two primary categories. You're looking at your alkene or your nonpolar pi bond in all of them, so that's kind of irrelevant. What we're concerned about is what's going on with our electrophile. And I already boxed in which one was the electrophile. Let's pretend I didn't do that, and we can address what that is in a second. So when we're talking about our electrophile, the electrophile needs to have some kind of positive charge. Most electrophiles have that positive charge hidden, right? So to be hidden behind it, there has to be something else connected to it. Right? That something else typically needs to be a leaving group. Why does it need to be a leaving group? Because it needs to take electrons so that I get the positive electrophile. Okay, so all of our electrophiles typically fit this kind of pattern. Right? The next part comes in when we're trying to look for patterns within the reagents. I think if you really zero in on what the leaving group is, it can help predicting your mechanism for how the reaction works. So if we look at the identity of the leaving group, if the leaving group is a good leaving group, excuse me, what you'll end up forming or going through is a three-membered transition state. Within your mechanism. If your leaving group is bad, you'll end up going through a 4+ membered transition state. Transition state or legitimate intermediate. Excuse me. Okay. So that is something to kind of pay attention to and watch out for as we navigate these things. Okay, so those are kind of the big summary behind it. That does get a little bit tricky because you then have to be able to apply that content to multiple different things that get kind of gross and difficult to manipulate. But those help to categorize things. And we'll see why that matters here in a second. So let's leave that alone for the moment and now go through and look at what our reaction is. We've got a nonpolar pi bond. The nonpolar pi bond is going to act primarily as a nucleophile, because we don't have a positive charge. You're looking at the electrons in the pi bond coming out to react. And you'll say, well, what about resonance showing a positive charge? Yes, that's true, but it's also showing a negative charge. So we have to go back to kind of the central structure, and the central structure is reactive because it has electrons. Those p orbital electrons are the ones that are going to drive this chemistry. Okay? The next thing that we do need to consider and think about within our nucleophile is it symmetric? Because if it's not symmetric, we do need to be concerned about our positives and negatives, because that's going to determine where your chemical reaction is going to happen. So we do have to pay attention to that. In this particular case, we are asymmetric. Okay? We're looking at hydrogen versus a carbon. That asymmetry is going to force some regiochemistry within this, so we've got to be a little bit more careful behind it. That regiochemistry is going to come from looking at our first worst resonance structure or our most useful, and that most useful is going to be placing the positive charge on our tertiary position and the lone pair or negative charge on our secondary. Okay? That resonance structure can now help us predict how the chemistry is going to manifest later on down the road. So we now have our nucleophile. We know something about how it's going to react. We need to push into looking at our electrophile. So now our electrophile has to come somewhere from the Br2 or the H2O. So if we were to look at those two structures, if I drew out Br2, I would get something that looks like this. And if I drew out H2O, I would get something that looks like this. What do you see in both of those structures? Okay. Most people look at those and see electrons. Okay. Bromine's got tons of electrons. The oxygen's got a pair of electrons. And if they have electrons, that means they should act as nucleophiles. So this seems to run very counter to everything we understand about these particular reagents. And this is where we have to dig a little bit deeper, particularly when it comes to one of them. Okay? We could go through and look at water because we're more comfortable with water. Oxygen is more electronegative than the hydrogen, so we could have the oxygen take the electrons away from the hydrogen, thus giving us a positive hydrogen. That positive hydrogen sure seems to match the system of what we're aiming for, a positive E electrophile. Right? This is where the language that we've discussed in class should help out. Okay? But another thing comes into play. What would the leaving group be? It would be hydroxide. Okay? Hydroxide's a bad leaving group. That would suggest this isn't going to work out so great for us. Okay? If we lean into it further, if we're looking at the hydrogen as being a positive, we shouldn't be calling that an electrophile. We should be calling that an acid. Okay? This is the electrophile addition section, and we're going to lean very heavily into that term of electrophile. Okay? So that sets us up to say, well, then water doesn't really make sense to be our electrophile, so that means it must be the bromine. Well, how could bromine possibly be an electrophile if it has a ton of electrons? And to answer that question, several of you are pushing on it, which is good. What I would do is move back to the chapters that we were just looking at. If this was my substrate, what happens? Bromine acts as a great leaving group, leaves, and as it leaves, what does it leave behind? A positive charge. Right? Do I still have a bromine in Br2? Yeah. Okay. Could it still act as a leaving group? Yeah. It could take the electrons away from that other bromine. And if it does that, what happens to the bromine on the left? It becomes very positive. The other one becomes negative. Okay? This particular reagent will haunt you all the way through second semester as well. Br2 acts as an electrophile, not as a nucleophile. And I would argue we've already leaned on this when we talked about the reactivity of our chloromethyl ether, and everybody circled chlorine. Chlorine can't act as a nucleophile until after it has left. Okay? So the reactivity sits back on the original atom. Okay? So if bromine's going to act as our electrophile, what happens? Our electrons come out, share with that bromine. We eject the bromide, and now we could start to have a conversation about our mechanism. And if we were to draw this out, we've already established where the electrons should go. They should be on that secondary, which means I should be forming the bond here to that first bromine. And then the second bromine chills out there with the negative. What else forms? Okay, and maybe you're not saying it because you know more about this mechanism and you're like, that doesn't form. You look at the arrows we've shown, what else must form? I need to have a positive charge. That carbon is missing electrons, it is positively charged. Okay, so what I've now done is drawn the arrows according to how I'm envisioning this particular mechanism work out. This is a possible thought process for how this mechanism could work. To decide whether this was the mechanism, what would we have to do? We would actually have to experimentally test it. Okay? And that becomes one of the challenges within OChem. Every mechanism we look at has had some theory pushed behind it to say this is why it works or this is why it doesn't. We could use this as a mechanism, right? And now we would go and test it in the lab, and what we find out is that it doesn't work the way we want. Well, when we're talking about it doesn't work the way we want, has to do with how we would visualize the product that comes out of this. Because we can't isolate intermediates. Okay, so what we should do is lean a little bit into the chemistry of what happened here. The pi bond reacted with the bromine, right? Where's the pi bond? Say again? It's not technically a lone pair. It's the pi bond. Where is the pi bond? in our starting material. This is between those carbons. Do better. Because technically, it's not between the carbons. Shocking. Where is it? It's in the p orbitals, which are above and below the plane of the molecule. So in the case of our drawing, we've got p orbitals in front of us, and we've got the other end of the p orbitals behind the plane of the board. What does that mean? When that pi bond reacts with the bromine, I could have that green bromine be wedged or dashed. Change the language a little bit. It's both wedged and dashed. When we run addition reactions, how many products are we going to get? At a minimum of 2. Okay? The relationship between those products, this is why we talk about chirality and relationships between structures, could be identical. So it may be something we don't have to worry about later, but it is something we need to be aware of. Okay? So we could go through and show that as wedged. Let's just pick one of them. If a cation, a true cation forms, I need to permanently stabilize that. What would then need to happen? The negative bromine should be able to come in where? On either side, because it's a carbocation, and a carbocation is stored in a p orbital, which is both in front of the molecule and behind. Which means if we look at this mechanism, we should get a whole bunch of different products, but the most important one to address is that according to our system of mechanism, I butchered the hell out of that drawing. Let's try that again. I should be able to get the scenario where both bromines are wedged or both bromines are dashed. That's what this mechanism shows. And when we go into the reality of testing this, that product doesn't exist. And since that product doesn't exist, what does that mean about our mechanism? It's wrong. Okay? So we have to alter our explanation of our mechanism to ensure that we can accurately represent the final products. Okay? And this is where we would go back to the patterns that I'm trying to call attention to. We've got our electrophile connected to a leaving group. If that leaving group is good, we need to form a 3-membered transition state or intermediate. What does that mean? No carbocation. I don't want the carbocation there. I'm going to form a 3-membered transition state or intermediate. Well, how could I possibly do that? To get 3 members, I've got 2 right now between those carbons, right? Okay, or between those carbons or between those carbons. To form a 3rd member, I need to make another bond between that positive atom and what? Do better than a neighboring atom. Can't be a hydrogen. Okay, so be less specific. What does that neighboring atom have to stabilize my positive? It has to have electrons. Okay? The hydrogen won't have electrons. They're occupied in the bond. So all I'd end up doing is a rearrangement. So what I want to do is find a neighboring atom that has electrons. Is there a neighboring atom with electrons? The bromine. And so that bromine could share electrons down. Okay? What would happen if we did that? And if you're drawing this, please don't, because we've got to go back and fix some stuff. There's my wedged bromine. Cool, but now I have a new bond between that bromine and that carbon. And what have I formed magically right there? A triangle, also known as a 3-membered transition state or intermediate. Okay? That's the point of recognizing the patterns behind that. This is also going to introduce some other things. Okay? We said that blue bond, now red, was wedged. What must that new bond that we just made be? Okay? For it to be dashed, let's consider this. Okay? Here's my sigma bond, straight line. Here's the bromine bond up there. For it to be dashed, I have to have this bromine be simultaneously above, wedged, and below. Can I make that bromine atom in both of those spaces? No. which means it can't be dashed. What does it need to be? It needs to be wedged. Now I've got that connection where it's wedged, which means when I look at that structure, that's going to be wedged. Okay? Should we backtrack and fix our mechanism, or do we want to continue this through to see where this ends? We're going to do both at some point. It's just a question of your preference. Just continue. Okay. There's another problem with what we've drawn. The bromine is now missing, not missing electrons, but if we calculate its formal charge, it's going to be positively charged. Okay? Does bromine want to be positive? No. So what's happening? It is already breaking one of those bonds. Okay? Bromine absolutely does not want to be positive, so it is an exceptionally good leaving group in this case. Since it's an exceptionally good leaving group, it's going to break one of those bonds preferentially. Which bond do we think is preferentially going to break? The red or the blue? The blue. Why? I would be forming a cation, air quotes, in the tertiary spot, which means in the next stage, my nucleophile with electrons can now come in and do a backside attack on that particular point. That means that nucleophile is going to come in and become what? A dashed bond. Okay? Kind of makes sense? So if we understand the mechanism, we can predict where those individual groups are going to align relative to each other. So one of your colleagues said, I heard that the ACS is all about stereochemistry. Yes and no. We use stereochemistry to leverage, do you understand the mechanism? That's it. Okay? I'm not asking you what's R, S, or even really wedges and dashes. Do you recognize when those bonds are being made and broken, the orientation that they are relative to each other? That's the biggest deal. That orientation only becomes apparent when we use wedges and dashes. Does that make sense? So it is stereochemistry and it isn't all at the same time. At least I would argue it isn't. You can disagree, that's fine. Kind of, sort of? Okay, so let's backtrack through this and fix. Okay? If this was our mechanism, we still formed a carbocation. And if we form a carbocation, I better get the two products where the bromines are both wedged, which means I have to change my mechanism such that I never form a carbocation. Okay? Well, how can I possibly do that? I need to go back to when that pi bond was broken, and I have to ensure that both bonds to that bromine are simultaneously made. So if I go back to my initial drawing where the pi bond came out and reacted with that bromine, hallelujah, great, that's one of them. I now also need to explain the other one. Where's the other one? The lone pair from the bromine comes back and hooks up with our carbocation, or our pretend carbocation. What does that mean, changes in our mechanism? Well, that carbocation that we drew disappears. Okay? The bromide is still fine, so we can leave that one alone. Okay? And now if we were to draw out our appropriate product, let's go ahead and color code it, I guess. We'll show wedge and wedge to our bromine. It's going to be positively charged if we wanted to throw in the lone pairs. If we're going to make those wedges, we need to also address that floating methyl. That methyl group cannot be left as a solid line because that's three solids in a wedge. That's not allowed, which means that methyl needs to be dashed to appropriately account for that stereochemistry. Okay? That sets me up with the proper intermediate. I've now shown a proper structure behind that, and now we could continue on to address the next part. Okay, which I didn't formally address. We talked about it a little bit. The nucleophile needs to come in, and it's going to break the blue bond. It's going to break the blue bond in our new drawing as well. All of that is legitimate. But the question now becomes, what is the nucleophile? So what should a nucleophile be? Something that can donate electrons. What is present that can donate electrons? The negative bromide. Sounds like a phenomenal idea. We could have the negative bromide come in and attack. We enter that into smart work, and we're going to be wrong. Okay? And that becomes a challenging question to deal with. This is some new concept that starts to come in within this particular section that we have to be aware of. Okay? What else is present in the solution? Conveniently, I erased it all. Sort of erased. Okay, brought it back in. We also have water present. Which one would you predict to be the better nucleophile? Bromide or water? I think I'm hearing the bromide. Okay, cool. Why? It's charged. We look at our rule sets. That absolutely makes 100% sense and logical. I agree with you. That's lovely. Why is water the nucleophile, not the bromide? Okay. We could go through and consider potential spouses. Okay. Male, female, doesn't matter. Imagine whoever your potential spouse is. Design them as best as you want in your head. Are you going to find that ideal person? Probably not. Why not? The concentration of that ideal person is very, very limited. So what are you going to end up doing? You will make changes to who your ideal person is based off of their other characteristics. So maybe you'll decide, you know what, I really wanted them to have long hair, but you know what? They don't have any hair. The rest of them was pretty cool. I'm going to partner with them anyway.
Some concessions.
Okay? So you could look at lots of situations like that. Guess what's happening here? Pretty much the same thing. It's concentration. When we go through and deal with this, the water is present in such high concentration that the likelihood of the bromide actually doing the reaction here is slim to none in comparison to the water. Does that make sense?
Say that? I might have missed it where it said that the bromide was a low concentration.
And therein lies the big question. While that is the truth behind the system, the water is there in much higher concentrations, how do we know the water is there in higher concentrations? Does it say? No. How are you supposed to know?
Because the water is smaller, so like have equal volumes?
Experience.
Yeah.
It's ultimately just going to be an experience thing. So if you're seeing bromine, elemental bromine, and something underneath it, that something underneath it is probably there in a higher concentration. Why might we think water was actually there in a higher concentration? Yeah, there it comes in. Water is actually acting as the solvent here. It's actually playing a dual role. It is both a solvent and a reagent. The solvent is there in massive, wicked concentrations in comparison to everything else. Okay? Again, we don't tell you it's the solvent. It's not obvious that it is. That's something that comes with practice and being able to navigate it. Kind of make sense? Okay. So what happens through the rest of this? We've now established that water's there in higher concentrations, which means water's our nucleophile. As a nucleophile, it needs to react. Where does it react? Does it react position A? Or does it react position B? It's going to need to react at position B, and this now has to do with the identity of our leaving group. Bromine is a phenomenal leaving group. Because it is such a good leaving group, that blue bond is already weaker. Okay? It's weakened that bond to the point where only position B becomes valid. Our water comes in, does a backside attack. The green bond is unchanged to our bromine. It's now happy with its full octet because it's gained our electrons. We should actually show the arrow. Okay, it gaining its electrons. The water comes in from the backside of that bond, which means it is dashed. There's our water. right? And then the methyl group that was dashed now gets pushed forwards, and it now becomes wedged, right? I crammed that in there, unfortunately, super, super tiny. I apologize for that. What's missing from our drawing? The oxygen needs to be positively charged because it does not, it was neutral to begin with. So it is going to steal electrons. It will preferentially steal electrons from the hydrogen. And then this would take us to our final product. We have our bromine, we have our wedged methyl, and then we have our dashed OH. Does that make sense? Yes?
Why did we have to do the bromide double bond? Because it seems like it would have made a carbocation and the water could have just come in without the bromide connecting or bonding and then unbonding to the tertiary carbon. Like, why did that intermediate?
And so this is where we float in kind of a strange gray space, because technically this reaction or this mechanism as shown isn't perfect, because we have examples that counterpoint this, that run against it. The vast majority of scenarios suggest that that bromine is doing at least a small coordination to the carbocation. Is that coordination formally a bond? Gray space, we don't really know. Okay? Based off of the evidence, the water can't come in and attack from the top side. You won't get the oxygen of our water and the bromide both wedged. That doesn't happen. Okay? So this mechanism is used to explain why that doesn't happen. Okay? As soon as you show a carbocation, you have the option for that mechanism to hold true. So you have to do something to show that that carbocation is being negated by the bromine. Okay? Do you want to invent a new type of coordination bonds that also simultaneously shows stereochemistry of wedges and dashes? I would argue that's probably why we didn't come up with another system, is because what kind of new bond could we draw in that space that would show that we aren't formally actually making a bond, but we also aren't not making a bond. We're hitting some gray space in between. So this mechanism allows us to best describe the relationship between those two things, and so we stick with it.
It's like an attraction because there's like a strong electronegative force and then the carbocation, but it might not officially like formally be a bond.
Yeah. So the other example that sometimes gets used, can I erase the answer? Yeah. Sometimes the other explanation you'll get would be something along these lines. So here's my carbon, okay, with their rough radii forming those bonds. Here's my bromines. What's the difference? The bromines are significantly larger, and so what's happening is that bromine, even once it makes that bond there, is large enough that it shields any potential attack from that side. Is it actually making the bond? I don't know. Do we have evidence to show that it could be making a bond? Yes. We also have evidence or another theory to say it's just big enough that it's preventing that interaction from happening.
So we just know that the water can't come in from the wedge side because basically the bromine is too big and it's like blocking.
So, and that's going to come down to which theory is easier for you to deal with. If you're going to say bromine is too big and blocks it, okay. Or you say you form the three-membered intermediate. Okay? Have I seen test questions specifically saying the three-membered intermediate? Yes, 100%. So if all you're going to do is say, well, bromine's really big, so it blocks that part of the cation, you're going to miss part of the content because ACS, the discussion on this reaction, absolutely still centers on the bromonium ion, which I didn't say yet, but we're going to come back to in a second, that three-membered ring forming. Okay? So you can use either explanation. both have merits. The bromonium absolutely, that three-membered bromine absolutely holds a pretty firm place in the literature for the discussion of the reaction. Okay, how firm? Firm enough that we actually name its existence. Okay, we call it the bromonium. Okay, what is NH3 when it gains a hydrogen? NH3 is ammonia, and when it gains a hydrogen, it becomes ammonium. Okay, that is actually part of the carbocation nomenclature. So when we're talking about bromine, bromine's elemental, we can make it bromide to make it negative, and if we want it to be positive, we can call it bromonium. That's where that name comes from. So you'll hear it referenced as the bromonium intermediate. Okay, and it doesn't have to be bromine. It could also be chlorine. Why could chlorine do it? It's a halogen. It's in the same frickin' family. The families all have the same chemistry. Chlorine is smaller, though. Okay? And if chlorine is smaller and it's creating less bulk, that might help to explain why we're actually forming a bond versus not. Okay? You could also look at iodine. Iodine's going to do the same thing. Did you have a hand
I was
up?
going to ask if there is an electrophile small enough to allow for topside attack in the product.
Yes.
There is.
Could like chlorine do it?
So, and that's an interesting question. It's going to come back to the different mechanisms on how we would navigate and run those reactions. Okay? That topside attack is going to happen when you get a bad leaving group. As soon as we shift into a bad leaving group scenario, you're going to get a topside attack. Right? So that topside attack is going to change the mechanism. You end up shifting away from a three-membered transition state. Okay, and note, I'm calling it transition state or intermediate. This is technically an intermediate. Okay, depending on how you want to define it, you could call it a transition state as well, but that's technically an intermediate because we're drawing it. Transition states, you don't draw. Intermediates, you draw. Okay? Transition states are an explanation of what you think is happening. That's what's happening with this diagram. We're arguing for a transition state explanation. Okay? So are there electrophiles? Yes. The conditions change. Those conditions change enough that you get a whole different system. Okay? Kind of makes sense?
So if it were like a methyl group or maybe like an amide, just something that were like a bad leaving group, we could do a topside attack.
Yeah, and we'll probably encounter a question if we keep advancing through this. I would bet we'll encounter one. If we don't, I'll make one up.
Do a carbine.
We can do a carbene. I'm not great with those off the top of my head, but I can do that. Drawing back the product that we got with this, we've got the bromine, the dashed OH, and this. It did say that there was 2 questions and answer the question in part 2. I didn't look at it, but I would bet the question in part 2 is, what's the relationship between the 2 products? Because they're only telling you to draw one of the 2 products. So the follow-up question is going to be, what's the relationship between this product and the other one? Where's the other one coming from?
Just did a wedge.
We did a wedge for what?
The bromine dash.
Yeah, so it's all coming with how the reaction occurred. So if we went through and drew the other product, what we're saying is that pi bond reacted with the bromine from underneath. So the bromine would be, that's a bromine, would be dashed. And if the bromine is dashed, what's the OH? It has to be wedged. Remember, it's coming in from the backside. So if your bromine is dashed, the OH has to come in from the backside of wherever it's at. It's going to be wedged, which means your methyl group ends up being dashed. So now what's the relationship between these 2 products?
The dash line, flip it, do it.
Okay, so this would be a case where you need that practice to deal with it. non-superimposable mirror images. These are enantiomers. I didn't hear what you said. All I heard coming from that direction was diastereomers. So, okay. Kind of, sort of? Okay. You said carbines. Oh, you want the chlorine one?
You have another one.
Yeah, I do. So we'll do that. Damn it. We're just going to do the chlorine one. I think I've got the other one, but I'm a little shaky on it. CHCl3 in the presence of, it's usually, I think, sodium hydroxide. So we would set something up along these lines. These would be our common kind of reagents behind this. We've got our alkene, again, our alkene or our nonpolar pi bond. I need to be saying nonpolar pi bonds because we can do these kinds of reactions with triple bonds as well. Though I don't think this one does. I don't think carbines do. Still going to act as a nucleophile, which means we need to find what? I need to find an electrophile. Okay, so I would go through and look at the remaining reagents. What's the most reactive thing I see? Pi bond we've already addressed. Sodium hydroxide is a strong base, guys. You should be jumping all over that right out of the gate. Okay? Which should be problematic because that's a negative. And if that's a negative, that most certainly is not going to react with the alkene because the alkene is also a source of electrons, which means that negative needs to react with, we don't have a carbocation. It needs to react with a CHCl3. We don't have a choice. It's got to do that. Okay? So, what is CHCl3? We got that. Okay? So what do you see within that could act as a positive? Why the hydrogen? You're breaking a carbon-hydrogen bond. The chlorines are electronegative enough that they're actually doing two things. They're making our carbon very positive, and they're making that hydrogen even more positive as well. And it turns out that the primary chemistry we get here is that the hydroxide comes in, removes the hydrogen, and shuttles the electrons onto our carbon. What happens? Cool, I get a negative. And you say, okay, still don't see an electrophile. You see an electrophile in the black box. The carbon is an electrophile. Why is that carbon an electrophile? Because the chlorines are great a leaving group, right? So what could happen? The chlorines could be leaving groups. What kind of leaving group is chlorine? It's a good leaving group. And because we've already had this discussion, if it's a good leaving group, what should we get? A three-membered ring. Okay, to get that three-member transition state, the electrons came out to form the bond with that weird-looking negative carbon. Where do I get the electrons to make the other bond? The pi bond came out to share electrons with that weird-looking negative carbon. Bond, bond. There's my carbon, there's my chlorines. And what I've done is known as a carbene. Okay, that particular reagent is a carbene. If we lean into this a little bit, you can actually push this all the way to this structure. And that structure looks really strange, ignoring the fact that my chlorines don't look like chlorines. What is the charge on that carbon? How do you calculate charge? Valence electrons minus number of bonds, which is 2, minus non-bonding electrons. What's the charge on that carbon? 0. There is no charge on it. But you want to call it positive. Why? It's missing its octet. That's the chemistry of your carbenes. Okay? We have an empty p orbital, which can accept electrons like an electrophile. At the same time, we also have lone pair electrons, which can immediately react backwards. If we now talk about this to the stereochemistry side of it, if we look at the final product that we've drawn, we'll black box it, sort of box. What is special about my purple carbons?
No methyl groups on them are the same. So, yeah.
Okay. What is special about those carbons? Keep going. Yeah. They're technically tertiary. Yeah. What else is special about them? Okay. This might be a useful, they're purple. This might be a useful statement. Okay. People have gone through that I've asked this before in the past. Every time I ask, what is special about these carbons, the answer is always the same thing. What was that?
No stereo.
Try again.
Stereo what? Does it matter? Does it matter?
Are those chiral atoms? Do they have 4 distinguishable groups? They do indeed. Which means I should be specifying stereochemistry with wedges and dashes. Which means those 2 new bonds that I formed, they should both be wedged or they should both be dashed. Technically, and both be dashed. Okay? Why? How the mechanism occurred. There's no way I can get that single carbon atom to attach both up and down to 2 different other carbons. It doesn't work. Which means when I go through and show my stereochemistry, that must be wedged and that must be wedged. Right? Or they both must be dashed. Add to this as well. Okay? When we go through and look at this product, because it happens simultaneously, those methyl groups that were locked in a cis configuration in our starting material are still locked in that same, I'm going to use air quotes on this, cis position in our product. They cannot freely rotate because it happens simultaneously. Does this become a big deal? Yeah, because when you look at your answer choices, you'll also get the other product where you show the methyls have rotated. How would you differentiate those products? It's going to come down to knowing that it happened in a single-step mechanism. So understanding the mechanism allows you to get to the answer. If you only understand the big picture stuff, I just make a 3-membered ring, that doesn't actually allow you to determine that extra layer of stereochemistry that can come with it. Yay! Kind of, sort of? Okay. So that is a case where you can have the carbene, where you have that single reagent coming in. Oh, you wanted the case where there were, you were just one, weren't you? You said just one? Yeah. So this lends evidence to the fact that bromine could be doing this also. Okay? Because we have a legitimate product here. We can isolate this. This is a neutral product. Okay? Fun thing about carbene chemistry is it's insanely reactive. Usually people that work with carbenes are missing fingers. Okay? Because the glassware that you use has to be perfectly smooth. If there's a chip in it, that creates enough of a site of friction that just the movement of gas over that surface can actually cause it to ignite. Okay? So it's a wicked reagent to work with. The other one that comes out, this is typically the one they use when they talk about carbines, but you could also see deep sigh because I don't remember. I think it's this. I think that's right. And then this has a lone pair and this is positive. So this carbon is negative. Okay. This is what's known as diazomethane. Diazomethane is very, very reactive. Okay. That's the substance that usually explodes.
What would you be able to do with that product?
Anything that required a three-membered ring. So if you wanted to study three-membered rings, you could use that as a structural piece. So what you're asking is a phenomenal question, and I love it. I don't know the answer. Right? But yeah, you're asking what can we do with these pieces? And unfortunately, I'm not a doer. I'm just the hey, you can do it. Even then, I'm pretty bad at that. But kind of makes sense? Other questions about what's up here? Okay. Do we just want to do, oh, I could go, hey, look at that. Hey. This is fun because we can do it backwards now. Okay. So, what do you need? X, we want to know what that structure was. So for me, this is where color coding comes into play, where if you have different colors, it can really help out. Okay, we're going to erase that plus. I'm being asked what reacted with this weird carbene structure. Okay, again, this is that weird one. That carbon has a 0 formal charge. Okay, but it has an empty p orbital, and it has an sp2 orbital with a pair of electrons in it. That pair of electrons is effectively negative. So we've got an empty p orbital, which is effectively positive, and a lone pair of electrons, which is effectively negative. The net result is that you get no charge. Okay, so it has both of those chemistries associated with it. If I'm trying to predict what reacted with this, the first thing I need to do is figure out where the hell this thing went in my product. So, where is it? So we're just trying to find that red dot. Tip of the triangle. So right there. Come on, pen. Why not? This has an ethyl and a methyl connected to it. So it can't be that spot. How about down here? Same issue. I have the methyl and the phenyl to it. So what you're doing is just zeroing in on the potential site and kind of backtracking your way out of it. Which then means, come on, pen. Stop it. That's got to be our little Rudolph. Which means in the course of this reaction happening, what happened? Those two bonds were made. Okay? That carbon acts as both a positive and a negative, which means what needs to happen back to these carbons, this purple and this blue? To react with a positive and a negative, what must we have? A negative and a positive, right? And the best way to get a negative and positive right next to each other would be a pi bond, right? So we could back our way out of this and say that we need a pi bond to connect these things. And where we would probably start, or where I would recommend you start, is just backing out as carefully as you can without making any tweaks or changes to the overall system. And that, ooh, I just added a carbon, didn't I? Yeah. Let's bend that a little better. Does that make sense? Okay, so we're trying to simplify as clean and quickly as possible. Okay? Some issues are going to pop up. If we enter this into SmartWork right now, we are wrong. Okay? And not because our drawing is necessarily incorrect, okay? But SmartWork can't grade it. Okay? When we look at a pi bond has these groups off to the side. The bond angle in all of those cases is 120 degrees. Okay? So the way SmartWork has set up the grading system is it looks at a pi bond and it divides it into quadrants. So as long as you have your bonds in those quadrants, it can now grade, because cis and trans becomes a thing we have to worry about. Okay? So that's what it's looking for. So if we go back to this pi bond and cut that up, it can't grade. Okay? It doesn't know where to place those systems. Does that kind of make sense? Okay, so then the next reflex that students would typically go through and do is go, okay, well, fine. If that's the issue, I'll just move that to the other spot. And now we fit within the quadrants. We're even showing proper bond angles. But now, SmartWork, again, probably says, you're wrong. Okay? And this has a lot to do with kind of the secondary context that goes with these things. Okay? When should you show wedges and dashes? When you have chiral atoms. Do we have a chiral atom? No. Okay? Which means the wedges and dashes should not be used. Does that mean the information held within those wedges and dashes is irrelevant? Unfortunately, no. They're still very, very important to us. So what we need to go through and do is convert this into a system that aligns with just solid lines. Okay? So let's start with this. Where do I want to draw that group in my product? We can call it 1, 2, 3, 4. Where do you want to draw it? Position 2, okay? I would agree with position 2 as well. We're getting rid of the wedge, but that's 2 carbons, so I've added that bond. Okay? Where should I add this one? That needs to go in at position 1 because it's connected to the same carbon. So once I've identified where our ethyl went, we're kind of locked into place with the other one. But now becomes the tricky part. Where do I want to place this methyl? Sure looks like I want to place it 4. What did the wedge mean? Out towards you. So if we take a look at this red group and that blue group, they're both wedged, which means they're both at you, which means they are same side of the pi bond. Is 4 the same side of what we identified as 2? No. So you have to make sure that you appropriately account for that stereochemistry. That blue spot is actually going to be position 3.
So did we rotate the molecule to get it this way?
So what you are ultimately trying to do is rotate the molecule so that you can get it into the proper configuration so that you can see it. So that becomes the proper orientation for my final answer. When I draw that in, SmartWork should be okay with it. Okay? I'm not allowed to do any bond rotations, which is why I can ask this question. Because if a bond rotations happened, I can't backtrack out to the exact orientation or to the exact single starting material. But the product I've got exhibits cis-trans isomerism, which means when I go through and react it with carbines, that cis-trans isomerism is maintained through the chemical process. Make sense? Again, is this stereochemistry? Okay. If we think back to what we called stereochemistry, it was interpretations of wedges and dashes, and oh, this is an enantiomer, diastereomer, R and S. We aren't really doing any of that. What we're doing is trying to understand where these things are in space. So it is an application of stereochemistry, but it's really coming back to how the chemical reaction works, what is the mechanism behind how it functions, and applying that to a new situation. That's what makes this challenging. Make sense? If we were looking at this as an ACS style question, you would absolutely see this as an answer, clearly because it's the answer, but you would also get all the possible permutations where everything had been swapped around. Okay, so all of your answer choices are going to look really, really similar. And so how you decide which one is correct is ultimately going to come down to how you're navigating it. You should be determining the answer before you look at your answer choices. That is your hands down best approach. So when you read a question, if you're like, oh, this is what needs to happen, don't look at the answer choices. Write down your work so that you know what the answer is. Match your answer to the answer choices. When you read a question and you're like, ooh, I don't know what the answer is, what should you do? That makes me a little nervous.
On a test?
Yeah.
You know the answer, just skip it.
Yes. Skip it. Okay? Move on. That's one that you were already hesitant about figuring out. If you look at the answer choices, 3/4 of the answer choices are misleading and they will guide you down the wrong path. So move on. Find all the questions you actually feel confident about answering the question to on your own, then double back and go through and look at all the other questions. Now you can start trying to reason through what are the differences in those answers, and hope a little bit of test-taking skill and structure interpretation can allow you to come up with those answers. Okay? But prove first and foremost what you know the questions are, or you know the answers to whatever questions. Make sense? Okay. Questions about what's up there? Continue? Too old. Okay, this one's got lots of parts. Fortunately, some answer choices are already there, so we can't limit that. Okay, but yeah, the way this one
Do you figure out anything on this one?
depends. The question is, what's the reagent?
Is it?
Yep.
Well, if it says worth 1 point, you have unlimited attempts, there's no attempt penalty.
Technically, multiple choice there is.
Why you could just keep on giving it to you find the right one.
That's true, but there's an increased penalty for multiple choice. Okay, and this says part 1, so I would bet what you're looking at is multiple parts, so that enough parts that all if you're doing is just guessing your way through, you're going to lose enough points that it doesn't count. Okay, but yeah, that's fine
But you give us 100 anyways if it's over 90%, right?
if it's over an 80%. And if this is just one multiple choice with 4 answers, I wouldn't be surprised if you immediately lose 25% of the points with one guess. Okay, I'm not positive because that's a different weird algorithm system behind how they calculate it. I believe the penalty percentages that I enter in are for things that have unlimited possible answer choices. When it becomes to multiple choice, I think they default their own system in. But that, again, is ultimately the wrong approach.
Whatever works, you know what I mean?
Is that going to work for you? That gets you a point here, and that removes your ability to learn and understand the content to be able to get it right on the final where you can't guess your way through it. That's the issue I would point out. So, how should you go through and figure out what reagent?
Figure out what happened.
First step is what happened. So, what happened? Elimination. A base is a good option. Okay, we do have to be a little bit careful with bases, because if our leaving group was an alcohol, do I want a base? No. So associating base with elimination isn't bad as long as you're acknowledging that it has some massive caveats behind it. Okay? What I would argue you should do instead of base is that when you do an elimination, what do you need to do? Break a leaving group bond and break a carbon-hydrogen. So breaking that carbon-hydrogen is typically reserved for the base. But if my leaving group bond doesn't break, having a base doesn't help me out. Okay, so recognizing the pieces that are necessary for that, I think, becomes more relevant. Okay, so in this case, do we have a leaving group? Yeah, bromine's a decent leaving group, which means adding a base is reasonable. We've got the first step already established for us. Adding a base could help. What kind of base do I want?
Something that
Cool. So you're saying sodium hydroxide. So if we look at that, we walk through here, your chemistry was you're looking for hydroxide. What is special about hydroxide? It is a strong base. It is charged. So it is strong. It is a base. It's also a nucleophile. It's actually a really good nucleophile. And given this scenario, we're now looking at a situation between doing an elimination and an E2. We want to do an E2 simultaneous because we have a primary substrate. That's going to be hard to run. Okay? So we need a strong base to force that off. But if I use hydroxide, that's a strong nucleophile, which is only going to further push, not E2, SN2, because the primary substrate is favored in the SN2, which means hydroxide is going to screw me over. I'm not actually going to get this product. I'm going to get the substitution. Okay? So I want a big, strong base. Bulky base is typically where I would go with that, but big is fine too. Okay, T-butoxide is generally better, so you could try and throw that in. Okay, but in this case, what you're thinking is big. You got me doing it now. I prefer bulky so much more. Okay, I want a bulky, strong base. That's my answer. So now what I can go through and do is look at my answer choices and say which of my answer choices provide me a bulky, strong base. Does that make sense? Okay, which is going to be a bit anticlimactic because as soon as I scroll and show it, we hit the solution, and I don't think there's any way around that because I believe you already attempted this one too. Yeah, and you already got it right, which means as soon as we scroll, oh, it didn't show it. That's lovely. Thank you. Okay, so if we look at our answer choices, we see RCO3H. Okay, we see HBr, we see H plus, H2O, and we see T-buto minus. We wanted a strong base to help us out with this, so we should be looking for something that's negatively charged. Kind of a silly question. There was only one thing that was strongly negative. Okay, so that would set us up with that as our answer choice. Okay, what should you be considering as practice working towards the final at this point? What the hell do all the other reagents do? Okay. So that's just trying to get some reagent practice in so that you're more familiar with what those chemicals do. Okay? Within those, just because I asked it, the O3 is a typical send-off that you're looking at a MCPBA clone. Okay, cool. MCPBA is used to make epoxides, and since I drew this incorrectly, from alkenes, our nonpolar pi bonds. Okay? HBr. HBr is a strong acid. Okay? That one becomes a little bit kind of tricky to deal with because the strong acid could do a whole bunch of different things. Okay? So what I would call attention to is number one, that we do have the H plus, okay, as being my primary chemistry, and then Br minus I would identify as a nucleophile. Okay? So depending on what it's being used for, it could do a variety of different things. That one becomes kind of a nebulous reagent. It could do a bunch of different stuff. The H plus and H2O, again, H plus is telling me I have that strong acid as above, and then we have H2O as my nucleophile. Okay? So I'm trying to call attention to those pieces behind it. Both cases of those strong acids, particularly in this particular unit, might stand out as being something that we could use when we reacted them with pi bonds, because pi bonds are a source of electrons. Those would react with H positives. So within this unit, you could see those as potential reagents. And then the last one we just addressed is our bulky base, our bulky strong base.
So is it not going to enter the nucleophile because it's bulky?
Yes. So this gets to the difference between what a nucleophile is and what a base is. Okay. To review that, you should go back and watch the lecture on nucleophiles and bases. Ultimately, bases react with hydrogens on the outside of the structure. Nucleophiles react with electrophiles, which are inside the structure. So if you need to get inside the structure, you need to be smaller. You have to pass by all of those reactive hydrogens on the outside. So your nucleophiles tend to be small. Your bases, if you're trying to make it act exclusively as a base, you want to make it big so that it can't get to the inside. Yep. Part 2, what changed? Right? So we could go through and say we formed the epoxide. That's fine. I would argue that's a step beyond what I've been asking you to go through and do. We broke the pi bond. I honestly don't know what I tried to spell there. Our pi bond, which is a fancy way of saying you did an addition reaction. Okay, once you've identified that you've done an addition reaction, what you can try and do is find the core pieces. Okay, addition, there's my 4 carbons, 1, 2, 3, 4. I've got 1, 2, 3, 4. So in this addition, the only thing I've added is that oxygen. I need to have a reagent where I add just an oxygen. I'm adding it to a pi bond. What charge are the carbons of my pi bond? Positive and negative, which means my oxygen needs to be both positive and negative. I need both of those components to contribute to that system. So what I could now go through and do is, depending on where I'm at within my content, is to find an oxygen that matches both this positive and negative, or if I zeroed in on the epoxide and happened to remember that we just mentioned what that was, we could look for that particular reagent. Does that make sense? Let's assume that we didn't do a good job memorizing our reagents, okay, but we have at least the passing context of positives and negatives. I need to go through and look at my reagents to see what chemistry I see within them. Okay, H2SO4, what do I see? This is going to give me H+. I wanted an oxygen that was both positive and negative, so that doesn't work. I have O3H. That sounds weird. We'll come back to that one in a second. Okay, we have OH-. I got an oxygen, and it is negative. Can I make it positive? No. That hydrogen's not going to rip electrons away from it, so that doesn't make sense. The H2SO4 gave me a positive hydrogen. The last one is giving me literally no oxygens, which means also wrong, which means it must be that middle one. What's going on with that middle one? This is where, if you're really good with Lewis structures, guess what you can do? You could draw out the Lewis structure. And in drawing out the Lewis structure, what are we going to find? What charge would I predict this top oxygen to be? It's probably going to be negative. Why? Resonance. It's connected to a carbon. It's going to pull the electrons away. That oxygen's going to come out to be negative. That's not going to get me a positive and a negative. What about my purple oxygen? Right? That one's an interesting one. Right? We could try and do resonance, right? And if we did that resonance, it would become positively charged. Okay? But we're having the electrons shuttle back and forth between those systems. Okay? If we look at the other bond, what's happening on that other bond? It's pulling on that bond equally. Okay? So the electrons in that bond evenly split both directions. Okay? Ooh, that could be a positive and negative. So that purple one looks susceptible. What about the green one? It's also positive and negative. Why would it be better? It's at the end of the structure as opposed to the inside. And guess what happens? Exactly that. We'll do a little bit of a rotation so you can see your mechanism on this. Here's our pi bond. See, I'm not the only one. Our pi bond can come out and react. We have a great leaving group that shuttles the electrons, that shuttles the electrons, that shuttles the electrons, that shuttles the electrons. And you're like, motherfucker, really? That many goddamn? Yeah. Yep, that's the system. What's the net result of that whole shebang? Our carbon double bond to that oxygen. We'd have those two lone pairs. We have a bond out to that hydrogen. Our green oxygen chilling over here is no longer connected to the structure or to the rest of those carbons, but it is connected out over there. Okay, and you would also produce a carboxylic acid. This intermediate, what can you tell me about, or not this intermediate, this product, what can you tell me about it?
Part of the structure.
It is part of the structure, yes, keep going. How many atoms? 3 in a 3-membered ring. This interesting 3-membered ring. What was our rule back? If we talk to our 3-membered rings, we're looking at an atom that has a really good leaving group. Is that a really good leaving group? Yes, frickin' yes. That's resonance stabilized. Yes, that's a phenomenal leaving group. That is fantastic. And you're like, but it's too big. We don't care about big, we care about stability. You've got resonance stabilization within that system that stabilizes that as a leaving group. Phenomenal leaving group. If you can recognize the patterns behind those structures, you can start to recognize what products need to come out of them. That's the beauty of looking for those patterns. Kind of, sort of? Okay, with that, we're done.